Hi everyone, this is Professor Abdi T. Abdalla. Welcome to my signal processing tutorial series where we explore key concepts in signal processing and work through practical examples to enhance understanding. In today's session, we will discuss the impulse function, or sometimes known as Dirac Delta Function. This is a foundation concept in signal processing. What makes the impulse function so important? We use it to model sudden bursts or spikes in systems, or any other phenomena that happen over a short period of time. So whenever you have such kind of phenomena, then we model it using impulse function. Okay, and in system analysis, for example, the impulse function is very crucial for studying how system react to sudden input. And this reaction is what we call the impulse response, meaning the output, how the system respond to an input, which is impulse in this case. And this impulse response, it provides valuable insights into the system's behavior and characteristics. As if you know impulse response, then you completely know the system. And you can describe a system in and out by using the impulse response function. This function is not a mathematical function in the usual sense. However, engineers and scientists have found great use. Why it does not appear in nature? Because the function itself is unbounded at the moment t is equal to t naught. As you see, when t is equal to t naught, then the function is unbounded, and making the function is not defined as other usual mathematical functions. However, the area under it is very well defined and is equal to 1. So the function is not defined, but the area under it is well defined, all right, and it is equal to 1. And that's why then we define impulse function based on its properties. We say delta t minus t naught is equal to 0 when t is not equal to t naught. So whenever, as you can see, whenever t is not equal to t naught, then delta t minus t naught is equal to 0. And the area under it is the integral from minus to plus infinity, delta t minus t naught. This is equal to 1. So most of the students are wondering why a given function is unbounded. It's not defined, but its area is. So this is quite an interesting to see. So let's start from ramp function. So considering a ramp which is rising from t naught to from 0 to a set value of 1 as the time increases from t naught to t naught plus epsilon. Okay, so if we differentiate once, if we differentiate this function f of t, getting g of t, then g of t will be an impulse. It will just be a pulse. It will be a pulse with epsilon, which is from t naught to t naught plus epsilon, and its magnitude 1 over epsilon. Why? Because the magnitude is equivalent to the gradient of this line. Okay, as the time increases from infinity to t naught, this function is 0, and so the derivative. And again, as time increases from t naught plus epsilon, and again it is constant, then the derivative of the function will again be equal to 0. The only non-zero derivative is between t naught and t naught plus epsilon, in which case we have the change in the vertical change, which is 1 in this case, and then divide by the horizontal change or change in the horizontal value, which is epsilon, and this is 1 over epsilon, change in y divided by change in x, in this case vertical and horizontal. So we have 1 over epsilon, and the width of the pulse is epsilon. So you can test from here, if you compute this area of this pulse, this will always be equal to 1, regardless of the value of epsilon. So on the limit, as epsilon approaches 0, they make this epsilon very small and close to 0, and then we are making 1 over epsilon approaches infinity. And in that case, then this defines the delta function. And this value here, beside a pulse, an impulse, then signifies the weight of the impulse function, which is the area under it. So this is a quite interesting definition or argument. Alternative definition. So alternatively, we can define delta function using the following integral relation. So if f of t is continuous at t is equal to t naught, then delta t minus t naught is defined using this property, where the integral of f of t delta t minus t naught dt is equal to f of t evaluated at the time of the delta. So when t is equal to t naught, then we are evaluating f of t at this time. All right, so the above operation is taken one step further. So if we take it one step ahead, we can also write f of t times delta t minus t naught, which is f of t naught delta t minus t naught, because this product will yield only a single value when t is equal to t naught. And this property is what we call the shifting property, which we normally use it extensively when evaluating those integral. This example number 1, I evaluate the following integral, so cosine 2t delta t dt. So using the shifting property, which states that the integral f of t delta t minus t naught dt equals to f of t naught. So now comparing the two equations, and you can clearly see t naught is equal to 0 in this case. You have delta t, so t naught is equal to 0, and f of t is equal to cosine 2t. So now plug in the values. We have cos of 2t delta t dt. This is the function itself, which is cosine 2t in this case, and then evaluated at t is equal to 0, which is the time of the delta, and this simplifies to 1. Right? Example 2, evaluate the following integral again, cosine 2 t minus pi over 4 delta t minus pi over 4 dt. Again, comparing the two equations, then we can see t naught is equal to pi over 4 in this case, and our f of t is cosine 2 into t minus pi over 4. So plug in the values of the function, which is cosine of 2t minus pi over 4, and then evaluating at pi over 4, and again this becomes cosine of 0, which is equal to 1. So as you have seen, an impulse function is a very powerful tool for analyzing and designing systems in signal processing, as we are going to see in the coming tutorials. So if you have any question about this specific tutorial, just feel free to reach out, but don't forget to share this video with others who might find it helpful. So if there is a specific topic, okay, in signal processing that you'd like me to cover in the coming tutorial, let me know in the comment, or you can just reach out via via email. Thank you for watching, and I will see you in the next course.